How about with 11 folds? What do you think? Yes? All right, so what do you think? This is hard, no? This is hard because the way we've been building it is that in order to figure out the next one, you would have to go, like, to get to 11, you'd have to go to 6, then 7, then 8, then 9, then 10, then 11, right? You could do it that way, couldn't you? Right, we could finish. At 6, it would be what? 64, and then at 7, it would be double that again, 128, and then at 8, it would be double that again, 256, 9 would be 512, 10 would be 1024, we're almost there, 11 would be 2048, something like that. You could do it that way, right? Build it up, but that's not efficient, right? I mean, like, it would be better if we had a function, right? Where what you would do is plug 11 in and it would spit the answer out, right? That would be better. And no function we have does this. No function we have. There's no function that will send 0 to 1, 1 to 2, 2 to 4, 3 to 8, 4 to 16, 5 to 32. Nothing we have. No lines will do it, no linear functions, no quadratic functions, no polynomial functions, no rational functions behave this way. You might think this function works. You might think f of x equals 2x. Maybe you think it's that, I don't know. Plug in 0. What happens if you plug 0 into that? You get 0, so that doesn't even work there, right? How about if you plug in 1? 1, it sends 1 to 2, doesn't it? And if I plug 2 into that, I get 4, right? But what if I plug in 3? I get 6, it doesn't work. If I plug in 4, 8, it doesn't work. You see? So like you might be able to find something that works sometimes, but you're not going to find anything that works every time without this new idea of a new function. All right? Does anyone know what it is? What the function is?
Yeah, so this would be f of x equals 2 to the power of x.
2 raised to the power of x. 2 raised to the power of x. So I want you to see that here. Look at this pattern. This is 2, which is 2 to the first power, right? 4 is 2 squared. What's 8? 2 times 2 times 2, right? So this is 2 to the third power. This one is another 2 multiplied, right? So that'd be 2 to the fourth power. And then 2 to the fifth, and so on and so forth. So do you see that the power is the input? The power is the input. 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 Oh, what about this one? That would, if it's going to follow this pattern, this would have to be 2 to what power? 0. Is 2 to the 0 1? Yes. 2 to the 0 is 1. Any number to the 0 is 1. Do y'all believe that 2 to the 0 is 1? No? I was explaining this to my daughter 3 days ago. Okay? I'm going to just make sure we're all comfortable with the idea that anything to the 0 is 1. And I'm going to do it this way. I'm going to go backwards from that table. If I go 2 to the third power, everyone agrees that's 8. 2 to the second power, that's 4. 2 to the first power, that's 2. Okay? I'm going to skip 2 to the 0. And then I'm going to go 2 to the negative 1. So do y'all remember that 2 to the negative 1 means 1 over positive 2? Do you remember that property? Exponents. If you have 2 to the negative 2, it means 1 over 2 squared, and that's 1/4. That if you have a negative exponent, you can write as 1 over that to a positive. That look familiar a little bit? So this is 1/2. The next one is 1/4. What's going on as I go from here to here, here to here? What's happening each time? I take 8 and I take half of it, right? I divide by 2. 8 divided by 2 is 4. Divide 4 by 2 and you get 2. What would naturally come next? Divide by 2. What's 2 divided by 2? 1. Okay, go again. What's 1 divided by 2? A half. What's a half divided by 2? A fourth. Understand? So does that make a little more sense that this would be true? Another way you can prove it is this, or convince yourself. If I said any number, let's say 4 to the third power over 4 to the third power. This would be 4 times 4 times 4 over 4 times 4 times 4. These would all just cancel out and just give you 1, right? But there's a property of exponents that says that that's the same as 4 to the 3 minus 3. So you're supposed to subtract these powers. But 3 minus 3 is 0. So 4 to the 0 should be 1. It's a different, I don't like this way, but this way makes more sense. All right, so this right here is our first look at what's called an exponential function. And what I want you to really understand here is where the variable is. Look at where the variable x is. Is it down on the bottom or is it up on the top? It's up on top, right? Up in the exponent. That is why we call it an exponential function. Do not confuse that with this function. This function is a parabola, right? Where's the variable? Down on the base. The exponent is a fixed number. We know this looks like this, right? Parabola. That's a parabola. And this doesn't work here, right? If we try this into that function, 1 squared is 1, not 2. 2 squared is 4. But 3 squared would be 9, not 8. 4 squared would be, well, that works, doesn't it? 16? But what's 5 squared? 25, not 32. So see, this one doesn't work. Works sometimes, not all the time. This one works every time. So, all right, we're going to have to wrap it up. I want to mention one more thing here. We're going to get into the study of these. We want to know how to graph them. We want to know their properties. But when we were making that table just a second ago, look at this. We had these numbers, right? Then it was 64, 128, 256, 512. Did anyone recognize these numbers? Have you seen these numbers before? 1632. Especially like 1632, 64, 128. Yeah. Well, some of them are perfect squares. They're not all perfect squares. Think about it in your life, in the real world. Have y'all seen these numbers before somewhere? What's that?
It's like the 24 game.
Oh yeah, that one game. Yeah, that's based on this idea.
Like ounces.
The what?
Like ounces and stuff.
Ounces? Are they always these numbers? How about your phones? When you get memory on your phones, what do they always give you as an option? Like how many gigs you want, right?
Yes.
And what do they give you as options? It's usually these numbers, right? Do you want the 128 gig phone or do you want the 256 gig phone, right? You have to pay more for it. Anyone know why they use these numbers? In that it's not just like, hey, you want the 500 gig phone? You know why they use these numbers? Anyone have? It has to do with the fact that these are all powers of 2. And when it comes to a computer only knows 2 things, on or off. Our phones are all just a bunch of switches that are either on or off. The video you're watching, right? That video is just a bunch of pixels that are either on or off. It's just zeros and ones. That's all any computer knows is zeros and ones. It can only be in one of 2 states. So everything in computers is what we call binary, which means that it's a power of 2. Everything is a power of 2. So when you go and try and get memory, the way they make memory, it must be in a power of 2. So it's got to be either 128 gigs or 256 gigs. Sometimes you'll see this. Have y'all ever seen 1 terabyte? Y'all know what a terabyte is? Okay, it's 1,000 gigabytes. So 1 terabyte, that's them rounding it basically. If you actually look at the actual data, like how many memory cells there are, it's going to be some power of 2. So anyway, I'm just showing you, this is why. It's because of the power of 2, binary computer. We're going to study this more next week, right? Next week. But this number right here can pretty much be anything. It doesn't have to be 2. It could be 3. It could be 10. It could be 1/2. It could be a fraction. So we're going to have to see like how these things work. All right? Do your rational homework. Yeah, the 2 is always going to stay at 2. Well, for this particular example, the 2 will always stay at 2. The power is the thing that changes. So the input is the power. Every time you plug a number in, it's just what that power on the 2 is going to be. 2 what? Yeah. So we have this new function now that if I plug in 5, right? What I'm going to do is I'm going to take 2 to the 5th power, which means 2 times 2 times 2 times 2 times 2, right? Which was 32. Yeah? Well, since I went over it with everyone, I'm not going to. Yeah, that's what I was saying. So it's good if you had it ready. Sorry, because I kind of blew it by giving everyone the answer. But do your homework for next time. Yeah, let me turn this off. That way we're not on. Was it even on? Yeah, it was on.